Okay, so I've started recording. Actually, this time let's not do like a recap of the previous thing because like it takes a lot of time to do a full recap of everything every single time. We'll probably do a recap next time so that we ensure retention. You know, over the period of time or whatever. Today we are gonna be like talking about syntax. Um Syntax of prop logic. Okay, so when we say syntax, right, what we generally just mean is like some sort of like a set of rules um, that you're gonna be playing with inside um, inside the framework of like prop logic. Okay, so for example, in the English language we have the English grammar, and there are certain rules that we have constructed. They are all sort of like conventional, like it's just like a bunch of scholars have agreed upon certain rules, that these are the rules that we will follow for the English language. um, and like some of these rules are also inspired by just looking at people talking in English and observing how they speak and all of that stuff, right? So like we have like English grammar. We have an analog of that in prop logic, which is what we call syntax. So I'll just demarcate this as grammar. um, Grammar analog, right? Okay, so it has like certain it sort of defines many of the key terms. Like syntax involves like defining what kind of um, like vocabulary you use. So I'll write that. uh, and then it delineates the rules for operating within prop logic. So we have like some formal system, there are rules within that formal system, and as long as you are playing within those rules, you're playing that. So think of it like a game, right? Like if you're playing a game of football, um, all the football players have sort of agreed upon the rules of football, and whatever they're playing is now called football. um, and like if for example I were to alter some rule, right? So let's say um, let's say I do the exact same thing, but I remove a lot of these rules. I remove the notion of a red card, I remove the notion of a yellow card, I remove the notion of offside or whatever, any kind of like sort of feature of the game, right? It's no longer, you're no longer playing football. You're playing something that's similar to football. um it might be like some like variant of football, but it isn't football itself. So similarly here we have certain rules, and as long as we are playing within those rules, we are doing prop logic. um so far so good.
So far, so good. Yeah. So instead of football, we can change the rules, make it with our hands, handball, or something like this.
Yeah, yeah, if you change the rules of football to allow usage of hands or whatever, it's no longer what we conventionally know as football or soccer or whatever. It's now some different game. Like it's some mutant version of football maybe, but it's not like the conventional understanding of football.
Mhm.
But yeah, so yeah, similarly like prop logic again, it's sort of like like it's sort of a game with rules, and like chess, like how we have like chess pieces and all of that. You have like rules in chess, um all that stuff. So here we are going to be like playing with propositions, operators, all of that. And then there are rules. So when we are trying to sort of give the vocabulary of prop logic, um, what we mean is like what are sort of the symbols that we are going to use when symbols or notation that we are going to use in like um, in this formal system. So we already know like for propositional variables, we already know that we use the English alphabet, right? From A to Z, you can use any of them. Um, but this restricts you to like 26 unique propositions, right? So, because there are only 26 letters in the English language, you're sort of restricted to 26 propositions. But there could be some argument that requires like more than 26 proposition unique atomic propositions or whatever, right? So for that, what you could do is um, you can like expand um, you can expand this um, you can expand it using some other notation. You can probably include something like a prime or a star or a star star. um, oh sorry, I put stars, a star stars, okay, a star star, whatever. So you can sort of endlessly increase this sort of like list of propositional variables, and you can basically come up with you can even use like I don't see any reason why you can't use like some other language's script as propositions. Like maybe you can use some Japanese character like I don't see why you can't use this. I don't see why you can't use a Hindi character, um, or like a Tamil character or whatever. Like any sort of like language, anywhere you have letters, you want to represent them with some unique propositional variable, you can use any of these symbols. So basically, you have like an infinite repository of possible propositional variables that you can assign to each of the propositions in like an argument. So basically, you'll never run out of propositional variables. Um, and then we have operators. I think this bit will be a little repetitive because we've already talked about like variables and operators previously, but that was in like sort of like a in passing. We covered the syntax in passing, so here we are like sort of formally like sitting down and trying to define it. So then we have like operators. Of course, we have the negation, the conjunction, the disjunction, the exclusive disjunction, the conditional or the implication, the biconditional. Um, yeah. So you have like all of these operators. Um, and then when you're writing in like natural language, you punctuate uh, whatever you're writing, right? Um, so punctuation will be like commas, uh, full stops, periods, colons, semicolons, etc. Okay. So these are like sort of the repository that you have um, when you are going to be dealing with propositional logic. Um, yeah. What you can also there are also like you can use proposition you can use a different propositional variable to represent some compound proposition. Like for example, um, let's say I want to write P and Q, okay, or something longer. Um, let's say P and Q, um, Z and P and Q and 0 T. Okay, so this is the proposition that I want to represent. And let's say, for the sake of example, that this particular proposition comes in the argument quite often, and you don't want to write this entire thing every single time. So what you will do is just define this as some different propositional variable. Let's say you want to define it as um, p hash or something like that, or like p sharp or something like that. Now this, wherever this comes, you will automatically replace it with this. That's kind of like understood, because that's how we are defining this propositional variable. So you can use a single variable to represent like compound propositions or whatever. So that's just a side note. Um, okay. Now, sort of, we've also like talked about different kinds of statements that are propositions, that are not propositional or whatever, right? So there are like, can you tell me the different kinds of statements that are there in the English language, and which of them is propositional, which of them is not propositional?
So do you mean the question, then
Yeah.
like affirmatives or just exclamations? They're not propositional.
Yeah, like the imperatives, the questions, the exclamations, they're not propositional. And like some assertive statement, like, the sky is blue, those are propositional.
Yeah.
So, but even then, like in the English language, when we write, um, let's take for example some statement, okay? Let's call this like, I don't know, some statement. Um, let's say the sky is blue. Okay, so this is the statement, and in English we have sort of written it in correct grammar, right? So there is like this word, there is the subject, and there is the predicate, right? So you can actually consider this entire thing sort of like the subject and predicate, right? Um I can write, I can rewrite this exact statement in like an erroneous kind of English. I'll just move this a little bit to the top. So I can write the blue sky is the, or something like, wait, I'll just say blue sky is the. So if you read this statement, blue sky is the, we sort of like intuitively and like instantly recognize that like there's something like wrong with it, like um, it's grammatically incorrect, because like the order of the words is all messed up. Like the way we speak English, this statement that makes no sense. It sounds like gibberish, and unless we put um, these, like put them in like the right order, this wouldn't make sense. So similarly, in propositional logic, of course, this is applying to like natural language like English, right? But even in propositional logic, you have the same kind of notion. So, for example, if I write P implies Q, right? So this is correct. But if I write P Q implies, right? So this, I don't want to use this symbol over here. Um, right? So this one is correct, but this one is incorrect according to like the syntax of propositional logic, and we'll get as to we'll get there as to why. So so for example, let's say if it is if you know, water is drain, like let's say P stand for something like water is falling from sky, and Q is it is raining. So this will mean if water is falling from the sky, then it is raining. That is kind of what we are trying to convey using this statement. But over here, if you read it like this, like if water is falling from sky, rain is it is raining, then that's something roughly how you will read that, you know. um, you'll read like, if water falling from sky, it is raining, then, or something like that. That makes no sense. um, but if you just switch the operator, and you see that, okay, this is what it means, like it means that if water is falling from the sky, then it is raining. That makes sense. But putting it like this, it makes no sense. There are other examples, like of course, if you have like a single um, propositional variable, um, and you have like a conjunction next to it, that makes sense again. Like if I say it is raining and something like that, like it makes no sense, like it sounds like the statement is incomplete, and grammatically we would say that that's like an incorrect statement. Same thing for or. um, you can also say something like p a negation symbol and q, right? So that's like it is raining, not water is falling from sky, something like that. Makes no sense. So unless you use the operators properly, um, the sentence actually translates to gibberish. Like if you don't use it properly, then the statement would just translate to something gibberish. And that's why I think like it's important to like understand. Yeah, yeah. Like, what do you think is like the obvious problem with these two constructions? Like, I'll try to see if you can work it out yourself. Like, I'll give you a hint. It's something to do with like. Oh wait, one sec. Are you saying something? Have you been saying something? Hold on, hold on. Mm, technical difficulties. Yeah, can you hear me now?
Yes.
How long have I been rambling without audio?
Uh, well, you stopped at the bit where you were talking about the uh, conjunction.
The conjunction? Okay, okay. Yeah, so I was just saying that, well,
Can't see your screen.
oh, you can't? I've shared my screen.
All I see is just 1 minute.
Let me restart.
Actually, I think I can.
Can you see it now?
Yeah, I just need to change the window. Yeah, got it.
Okay, yeah. So, did you hear till this part? Till the implication thing?
Yes, I heard that bit, and then I heard I didn't see this bit. You had the negation between the P and the cube. You were halfway through, just explaining that you said that when you have the conjunction after the P, it's still valid.
No, no, no. I didn't say it was valid. So I said like this would also be like incorrect. Um, because like let's try to you know, sort of translate the statement, right? Let's say it is raining, and if I say it is raining and I just leave it there without, you know, any further any further statement, it actually doesn't make sense what I'm trying to say. Like it sounds like I'm making like an incomplete statement. Um, and like there's like an obvious problem with that, and there's also like an obvious problem with like using or saying something like p, or like it is raining, not or or something. Yeah, it is raining, not the sky is blue, or something like that. So if I just like literally translate these statements, I'm gonna get like some gibberish. Like either it is going to be like um, either it's going to be incomplete, or it's gonna sound like that's completely gibberish. And what I want you is to tell me, like, we'll see if you can catch on why this is happening. What's, um, why is this not making sense?
It's not making sense because when you put it into the natural language,
Mm-hmm.
there's for the first case there's something missing
Mm-hmm.
because it's p
Mm-hmm.
and then in the second case it's between p and not p not q. It's like there's missing some sort of connective between the two.
Right.
Like if you
Yeah.
translate it into that language, it's just like gibberish, yeah, as you
Yeah.
say.
And the other thing is that there is something very specific to do with like the nature of the operators that are being used. So what would that be? There's an issue that is related to the nature of the operator being used.
So I'm guessing, well, the first one is well, the first one is a binary operator, so it
Exactly.
needs, and then the second one is a unary operator, so it only works on one variable, and the first one will work on two variables, but we're missing a variable in the p and.
Exactly. Yeah, exactly. So this conjunction is a binary variable in this. Sorry, it's a binary operator, which is basically, it means that it connects two atomic propositions, um, and like a unary variable, like the not variable, unary operator, like the negation, would just be a like it's just going to be attached to a single proposition. It makes no sense to put it between two propositions, not two propositional variables. So that's exactly the answer I was expecting. Okay, so by and large we've sort of understood that there's something wrong with the way um, like these two statements are sort of constructed, right? So, and what we'll do now is just lay down all the rules for what we call a well formed formula. And this is a very important concept. A well formed formula. Wait, why is it not yellow? Yeah, like a well formed formula. Okay, so basically, a well formed formula is abbreviated as WFF. Okay. Um, it's basically like a grammatically correct proposition. A grammatically correct in the sense it follows the syntax of propositional logic. It follows the rules of propositional logic. So if a statement, a proposition, is constructed according to the rules of propositional logic, then it is a well formed formula. So we can just write that, right? Uh, so something like a proposition constructed, one second, My PC is dying. Constructed according to rules slash syntax of prop logic. Okay. So yeah, just a well-formed formula is a proposition um, constructed according to the rules of or syntax of propositional logic. Okay. So I'll just give you examples of well-formed formula. Um, Actually, I'll give you the example of non-well-formed formula, and then we will sort of go into how to construct well-formed formulas. So a non-well-formed formula is just the examples I gave earlier. It's just a p and or a p negation q or like something like that. Just a disjunction symbol before like a propositional variable. All of these are like non-well-formed formulas. So there can be like an endless example list of examples. So we have talked about like rules, right? So what are the rules? So let's now just lay down the rules of um, forming WFFs. Before we get into this, are there any like questions you want to ask or like something isn't clear?
So far, it's pretty clear for me. You said it's going to get difficult, but so far I'm following.
Okay, cool. I mean, yeah, I don't want to like it might just not get difficult, right? Like, um, yeah, like it could be. I think it's like all of this stuff is like very easy. Um, but yeah, like yeah, this is like yeah, it won't be very difficult. Don't worry. um,
So I'm
so.
guessing I can guess like the first two rules. I'm guessing from
Mhm.
what we saw, like a binary operator must connect two propositional variables. Would this be one?
It's actually written a little bit more like sort of like how do I say this? Uh, a little more like systematically or whatever. Um, and I'll show you what the actual system is. So, um, so these since these are rules of propositional logic, we will just call them like I don't know, like number one, something like that. Okay. So the first rule is that any single capital letter is going any single capital letter um, yeah and like even if I don't yeah, it doesn't have to be capital. Any single character is a well formed formula. Roughly people always say, oh, it has to be like English or whatever. I'm more liberal. I'm like, okay, any character you want to use, you can use it as a propositional variable. I just don't care. So any single character, um,
So for example, P star, that still counts as a single character, right?
yes, that still counts as a single character.
But I cannot, for example, put two uh, letters together and use that as a single variable. For example, AB, ABC, and use that as one thing, right? That
I
won't
mean,
work.
there's nothing stopping you, but that's just going to be a little confusing. If you have like two letters of the same, the same case, like you have like capital A, capital B, it's going to be confusing. Like, are you talking about one variable or like are there two variables? It's sort of confusing. But if you change the case, then that's fine. So if you're
Okay.
like a superscript A or something like that, or A superscript 1, B superscript 2, something like that. That's fine. So as long as it's like a single character, in the sense that um, like a character and its superscript or subscript is going to be like one character, um, but like something like A B won't be uh, a single character. There'll be two characters. So this is just to avoid confusion. So yeah, so like a single character is a well-formed formula. So I can write examples like P prime, P star, etc. Okay. Um, and the second rule. Okay, by the way, all of these rules are assuming that this character is representing a proposition. Like, of course, if you're using this character to represent a question, that's not going to be a well-formed formula. It's not even a proposition. So, if it's not even a proposition, it's beyond the scope of whether it's like a properly constructed proposition or not. Like, if something is not a cake, then it is outside the scope of whether it's a chocolate cake or a vanilla cake. It's not even a cake, right? So if something is like, yeah, if this character is used to represent a question, it's not even a proposition. So it's beyond the scope of whether it's even a well-formed formula or not. So like, short answer is it's not a well-formed formula because it's not a proposition. So all of these rules are sort of uh, operating under that sort of background assumption that you are using them to represent propositions and not some non-propositional statement or string of characters. Okay. So that's rule one. Um, okay, so let's say so let's use like a you know let's use like alpha to represent a formula. Okay. So alpha is like some any proposition. So alpha is called sort of like a meta linguistic variable. Um, 1 second. You don't need to remember this part because it's more of like mathematics, like formal study of like uh, logic or whatever. Like for the sake of learning propositional logic and not going very like mathy, you don't yeah. I mean, if you are interested, we can go into that too. Uh, but yeah, linguistic variable.
Alpha, I think it commonly represents in maths proportional, if
Yeah,
I'm correct.
if it is used for like two quantities, like I don't know, g like some force is like directly proportional to mass and acceleration. It represents that, but over here it is just used to represent like any formula, like a yeah, any arbitrary formula. Now this alpha can be replaced with p, it can be replaced with q, it can be replaced with anything. That's why it's called a meta linguistic variable. Like this variable itself is a variable which is like representing any propositional variable. Okay. um so that's why we are using like alpha over here. So alpha, so the rule number one is any single character is a well-formed formula. um, the rule number two is that let's say alpha, like if alpha is a well-formed formula, then not alpha is a well-formed formula. Okay. So for example, if sky is raining is a grammatically correct proposition, then the sky is not raining is also a grammatically correct proposition. Or let's say it's not the case that the sky is raining is also a grammatically correct statement, right? So similarly, if alpha is a well-formed formula, then not alpha is also a well-formed formula. Okay. That's rule number two. So far so good?
So far, yeah, so good.
Okay. let's go to number 3. Uh, so number 3 is sort of going to be like, it's going to be sort of similar. Like I can just call this like as number 3, and then like number 3 can be like the broad thing, and there are like 3.1. And the assumption of number 3 is that if alpha and beta are well formed formulas, okay, that's the sort of assumption, then 3.1, alpha and beta is a WFF. Can you guess what's 3.2?
Alpha or?
Yes, alpha or beta is a WFF. Keep going.
Then we can just go, so alpha, and then I guess you can put exclusive disjunction.
Sure.
And after that we can try a conditional.
Sure.
And then we can try a biconditional.
Sure. Okay. So yeah, that's rule number 3 basically. So whenever you have two propositional variables alpha and beta, which themselves are well formed formulas, then a conjunction or any binary operation between them is also going to be a well formed formula. Just the same way how P is a proposition and Q is a proposition, and P and Q is also a proposition. Here, P and Q being well formed formulas means that a conjunction of P and Q is also a well formed formula. Okay. And then we go to the final rule. And the final rule is kind of tongue in cheek. It's basically that there are no other well formed formulas. Okay, so there are four rules. Three of them define three of them define what is a well formed formula, and the fourth one says these are the only well formed formulas, nothing else is a well formed formula. Okay, so far so good.
Yeah, so far so good. So 4 is just saying that there's nothing else.
Yeah, those are the four rules.
Yeah.
Yeah. Um, yeah. Okay. So yeah, we can just like I think we have already talked about how like the smallest well formed formula is going to be like an atomic proposition. So like the sky is blue is one proposition. It's not a conjunction, it's just an atomic proposition. So that is going to be like the simplest well formed formula, and from there you can construct compound well formed formulas, and each compound well formed formula is further made up of atomic well formed formulas, or um, you know and like yeah, they're either atomic propositions themselves or themselves are compound propositions. Okay, so Yeah, that's pretty much the sort of um, uh, there's some other things. For example, yeah, like basically this is how you construct well-formed formulas, and anytime, like you will, and the reason I'm mentioning this is that this often comes up in like debates. If you want an example, there is a video of Ask Yourself and Avi discussing. Do you know Vegan Food Soldier?
Yes.
Yeah. So Avi and Isaac discuss vegan food soldiers' argument against killing predator or predators. That's a video on the AY Discord archive. You can probably watch that video as sort of a reference for this. Um, and the reason is because one of the premises of the argument that vegan food soldier gives is not a well-formed formula, and that is one of the main critiques of the argument, that it doesn't even contain well-formed formulas. And because it's not a well-formed because it does not contain well-formed formulas, it's not an argument. And the reason I say it is so that we can go back and make an an upgrade to the definition of an argument that we started with. You remember that?
Yes.
Yeah.
We we're on revision number one.
Mm-hmm.
So at
So
least a set of propositions such that at least one proposition is a premise and at least one is a conclusion.
yes.
I think that's what we got.
Yeah. So what we will do here is we will make an upgrade. We will just upgrade this to reflect our latest concept. Um so an argument is a set of WFFs, and the rest is the same. Okay. Um, yeah. So that's
So
revision two.
so it's a set of well-formed formulas such that at least one proposition is a premise and at least one is a conclusion. Is that how we would
Yeah,
say it out loud?
you can say that as one proposition or one well-formed formula. Uh, yeah, and yeah, like since we have already replaced proposition with well-formed formula, you can probably just say well-formed formula. Okay, so nobody
Okay.
is going to give you like heat for that. Like this is just a set of well-formed formulas says that at least one well-formed formula is a premise and at least one is a conclusion. Then that's an argument.
Okay, cool. Got that.
Okay, we've sort of arrived at a very precise definition of an argument at this point. Uh, yeah.
I've got one question on the rules.
Okay.
So, so where would something such as alpha and not beta, uh, would that where would that come in within the rules?
Oh yes. Okay. Yeah. That's a nice question. Okay. So let's deal with that. Let me switch my colors. Um, okay. So let's say alpha and not beta. Okay. So I'll ask you this question: is alpha a well-formed formula?
Yes.
Alpha is a well-formed formula. Is not beta a well-formed formula?
Um, so a well-formed formula, any single character is a well-formed uh, formula. That's our criteria, right?
That's right.
So so we have a character and an operator to the side of it. So
Mm-hmm.
does that still count as a single character?
I
Or
mean, this is the character and this is the operator. So this is a well-formed formula. And according to, remember rule 2 is that for any formula alpha, the negation of that formula is also a well-formed formula. That's rule 2.
okay, cool. Yeah, I forgot about rule two. So
Yeah.
then, yeah, that assuming that alpha and beta they're not questions, that they're propositions,
Yes.
then they're both well-formed formula, and then not beta is also then based on rule number two, and then based on rule number three,
That's
the
right.
whole thing is a well-formed formula.
Exactly. So here we have alpha is a proposition according to rule number 1. Beta, not beta, is a proposition according to rule number 2. And the conjunction of alpha and not beta is a proposition from rule number 3. Okay, so this is a well-formed formula. Okay, I think you're getting it now.
Yeah.
Okay, so there is one more concept of uh, like what's sort of the uh, yeah, like what's sort of the main operator within a well-formed formula. Like for example, if you have um, and I think we have talked about this during the ambiguity thing, that often the main operator is sort of determined by the author's intention, rather than like some fact of the matter. Like whatever the person is saying, it depends on what they're saying as to what the proposition actually is. So let's say you have something like P and Q, um, exclusive XOR, um, T, double implies Z. Okay. So here, so for example, the main operator is the operator that is connecting. Um, yeah, like what do you think is the main operator over here?
Uh, I'm guessing. Well, when you say over here, what are you referring to?
Over here, as in this example.
So, so I'm guessing. So we've got the two things which we do first, the P and Q, and then we have the biconditional between T and Z. But
Mm-hmm.
I'm guessing the main operator is what connects them. So the
Yes.
exclusive disjunction.
Yes, exactly. So this is the main operator over here. Okay. So even though we have like three operators here, there's only one which is sort of the main operator. And what the main operator is, um, in sort of like you know um, in some given proposition, it can be sort, you can do this just by intuitively, but you can also like look at sort of um, the construction of it. So for example, P and Q both are well-formed formulas. Therefore, this is a well-formed formula. According, so again, this is rule 1, this is rule 1, this is rule 3. Okay. Then you look at this. Um, this is a well-formed formula. This is a well-formed formula. Again, rule 1, and then the entire thing is also a well-formed formula according to rule 3. Now, there are two well-formed formulas which are connected by this. So this entire thing is a well-formed formula. And since the biggest well-formed, so it's sort of like the largest well-formed formulas over here are like these two, and they are connected by this. So that's how we determine that this is the main operator. That sound good?
Yeah, I got it. So you sort of think of in parts, sort of.
Right.
So you can consider different parts and then build it from there, and then consider the whole
That's
based
right.
on the main operator.
That's right. Yeah. Now I can give you a longer example, and I'll let you uh, play with it. So let's say you have Q. sorry, Q or R, uh, and S or T or Z. Wait, that looks like a 3. Z or um, Q implies I don't know, G. Okay. What do you think? Is this a well-formed formula?
For me, it looks like it is.
Okay, let's try
Even
to
though
prove it.
so we have two main operators in this one, so it's a little bit different. But
Okay, so is that a well-formed formula according to the rules?
uh, so according to the rules didn't say that we can have two main operators, but
So,
so then I'm guessing not then.
yeah, exactly. So, rule number 4. Rule 4 is that uh, there is no other way to construct a well-formed formula apart from the already defined rules. Okay, this is rule number 1 to 3. So, this is not a well-formed formula. However, if I make some modifications, I can turn this into a well-formed formula, and that modification is just going to be like punctuation, right? So I can put like a bracket over here and a bracket over here, denoting that this entire thing is one well-formed formula, and then this is a well-formed formula, so that this becomes the main operator, right? So we have two well-formed formulas, this entire big one and this one. So we have two well-formed formulas connected by a disjunction. Is that a well-formed formula?
Yes, now it is. Now that you've added the brackets in, it
Exactly.
seems like yeah.
Exactly. Now that I've added the brackets, it's now a well-formed formula. The other way again is to just move the brackets to somewhere else. If I move the brackets to here, is that a well-formed formula?
Yes.
Okay, can you try to show how that this is a well-formed formula?
So, yeah, what we have inside the so the first C or T or 1 minute. Yeah, the so to show, I guess. Oh well, the would we need to put brackets somewhere between the in the first bracket we have C or
Yes.
T or T. Okay.
So, okay. Try to think about. Technically, yes, according to the rules, but for things like conjunctions and disjunctions, there is a rule called there is a rule of replacement, which is called what's that? Was it association or commutation? I don't remember. We will get there. Uh, but basically, the answer is yes. You actually do need to put a bracket over here, but when you have the same operator, it actually doesn't matter what the order is. So you can, whether you put a bracket over here or whether you put a bracket over here, uh, the truth value ultimately is preserved. Okay, and you can try to you can take this as homework. Prove that S or um, what did I write? S or T or B? T or Z, okay. S or T or Z um, is equivalent to S or T. Yeah, I've sent that question to you. But yeah, short answer, yes, you need to put brackets because if you are going strictly by the rules, you can only connect, like, yeah, you need like brackets within them. But you can eliminate the brackets because the truth value ultimately evaluates to the same thing. Um, yeah,
So I'll do that by drawing out the truth values, right, and showing that they're
exactly.
both.
Yeah, exactly. Yeah. Okay, now let's continue. So try to prove that this is a well-formed formula.
So then inside the yeah on the brackets on the left hand side, the T or Z, that's a well formed formula, and then
Oh, wait,
uh,
come again.
inside the brackets on the right hand side,
Mm-hmm.
the T or Z,
Mm-hmm.
that's well formed,
Okay.
and then the S or what we have. So we can consider that as one variable, the T or Z, and then the S or T or Z. So then that is also all well formed inside.
Yeah. So I'll just add one thing. So whenever you are starting to prove that something is a well-formed formula, okay, let's just write down the sort of like how to prove something, how to check for well-formed. Yeah, how to check for well-formed formulas. Okay. So I'll just write how to check for WFFs. Okay. Step 1. Okay. Uh, Step 1, identify atomic WFFs. Okay, that's step 1. Step 2, um, identify um, okay, let's go back to this. Okay, so what will be the first step? Apply the first step over here.
So identify atomic well formed formula. So we have an S,
Okay.
and then the T and the Z there,
Okay.
and then the Q and the J.
Okay.
That's step one done for.
No, we have
for
more left over here. We
okay.
have Q and
And
R.
then, yeah, so also Q and R.
Okay. Then.
So then the that step one, identify atomic well formed formulas we've done.
Mm-hmm.
So then step two, I'm not sure what to do, right? Step two again.
Identify compound well-formed formulas.
Okay.
Okay. So
So, so the compound we have is T or Z.
okay. So that is a well-formed formula. This is a well-formed
Yeah.
formula. So is this a compound well-formed formula?
Yes.
Okay. So this is all step 2. Okay. Step 2, you're identifying all the compound well-formed formulas.
Okay. Then on the left hand side we have Q or R. Or
Uh-huh.
yeah, you're pointing at the other one, but yeah, Q or R on the left side.
Okay. This is a well-formed formula. Then.
And then we have the implication
Okay. This is a
conditional.
well-formed formula. Then.
Yes. So then we have so we've identified all of the compounds, right?
Yes.
Uh,
No,
but
no,
then we
no.
have
We have
we
one
we
left.
have we have the yeah the next one, yeah, up a level, we have uh, between the two brackets,
This one.
yeah,
That is a well-formed formula, correct?
and then we have the main operator left,
Yes.
and then we using our rule number 3 from the rules of forming well-formed formula, then that is a well-formed formula.
Exactly. That's how we do it. Okay.
It's
So
easy to miss something, I think.
yeah, it's you need to be a little alert, but yeah, like this is just like a starting phase, right? Once you do quite a few of these examples at the end, like eventually it'll sort of become second nature.
Cool.
uh, I'll just write check for check rules. Okay,
Awesome.
because
Yeah, yeah.
because like you once you've identified well form formulas and you've identified the compound well form formulas, you need to tally it with the rules to see if they are following it, and if there is any compound well form formula which is not um, you know properly formed in the larger. So for example, this entire thing could be a well formed formula, but this thing could not be a well formed formula. Like there could be there could be a negation symbol over here. So even though this is a well formed formula and this is a well formed formula, the entire thing is not a well formed formula. So you need to check rules and see if all the rules are followed.
And then would there be a step number 4?
No, no,
Identify
that's
the
all.
main.
That's all.
Uh,
Yeah.
uh,
E-
Identify the main operator. That's not an extra step, no.
No, I mean, if the goal is to check whether this is a well-formed formula, you don't really need to identify the main operator. You will identify the main operator as a consequence of identifying whether this is a well-formed formula. Because the last operation that you're checking, like, so the first one you went for this, and then you went for this, and then you went for this, and then the last operation that you looked at, that is going to be the main operator every single time.
Cool.
So yeah, you identify the main operator as a consequence of checking whether the entire thing is a well-formed formula.
And the check the rules, does that come after you've already identified the main operator?
Yeah,
So,
sort of. Well, yeah, you sort of identified the main operator and then you run the entire thing through the rules and then you see whether this is a well-formed formula.
okay. So yeah, so before, so like you
Yeah,
at first you do all of it and then you go
yeah,
through all of it, checking the rules.
yeah. But this is like this is sort of like a like this is not like I'm not mentioning it in the steps because like you will do it anyway, like even if you don't even if you don't know that this is this is the main operator or whatever, you will eventually get at whether this is the entire thing is a well-formed formula or not. Like yeah, this is just like sort of it's happening by process. So I'm not writing this as a step, but it happens as a series of events. So as you perform the analysis, at some point you're going to identify the main operator, but that's not like a step. It's sort of like it's just an event in the process.
Got it, yeah.
Yeah. Okay. So I guess that should be enough for today. Uh, like we have done some important stuff over here. Like this is sort of like the base, like sort of the very foundation of prop logic, like the syntax and semantics.
Yeah. And yeah, people, I'll try the question you gave me
Yeah.
earlier on. People can try that. And also, I can link the video which recommended in the description so people can watch the video
Yep.
between with RV and Ask Yourself and
Yep.
see if they can identify where it was not a well-formed formula from Foot Soldier.
Yep. That's right. Yeah.
All right, great.
Cool. Yeah. I'll see you next on Thursday or Saturday.
Yeah, whenever. Yeah,
Cool.
we can.
Yeah.
Yeah, we can decide.
Yeah. So yeah, cool. I'll see you around.
Perfect.